Hello everyone, this video is for KTCE math problem whose employee year is 2024. KTCE stands for Korea Teacher Certificate Exam. A person who wants to work at a middle school or high school in Korea is supposed to take this exam and is supposed to pass this exam. Okay, on this video I'm gonna specifically deal with the B type, major B type, problem number 10. This is about convergence of sequence of functions. Since this is a sequence of functions, the function has indices n. So for each indices, it has each function. Okay. Sometimes it diverges, but sometimes it converges to a specific function. Let me say f of x here. The way of converging to this target function, we have two cases. The first case is where for each point x in the domain, when n is large enough, then the difference between target function and the sequence of function, let me say the index is large enough, larger than the capital N, then their norm can be small as you want, say epsilon. So for a given epsilon, given some positive value, and for each x, so this capital N actually depends on the point x. So which x I choose, and then this capital N could be different. Actually, this capital N also depends on the epsilon. So capital N is a function of both x and epsilon here. We say this is a pointwise convergence. For the second case, which is more stronger, for a given epsilon, it's the same given positive number epsilon here. We don't care about, we don't choose an x here, but for a large n, when n is large enough, then the norm of the difference between target function f of x and the sequence f n of x can be small as you want. Okay, so in this case, this capital N does not depend on x, but it only depends on epsilon here. So in this case, this is more stronger case. So for the whole x in the domain here, this norm is less than epsilon. This is called uniform convergence. Either pointwise or uniform convergence, we need to know its target function. We have to assume there is a target function, some target function, and then we have to calculate the norm of their difference. This is a sketch of our strategy for this problem. On this problem, we are required to show the uniform convergence of the sequence of function. Okay, let me dive into the detail of this problem. The first point is to set the target function f of x. Okay, so let's take a look at the sequence of function f sub n of x here. It has two parts. This rational function part and this summation part. For this summation, I'm going to rewrite this part as I'm going to pull out the same vector, say e to the negative kx power here. So I can rewrite on this way, e to the k times e to the minus kx power, and then what's left is 1 minus e to the minus x. Okay, so k goes from 0 to n minus 1, and what's good thing here is this vector does not depend on index k here, the summation index k. So we can pull out this part outside. Okay, and what we have is this rational function part plus 1 minus e to the minus x times, and its summation, and the k power is the same, so I'm gonna use parentheses x times e to the minus x power and its kth power, summation k from 0 to n minus 1. And as you can see that this is a sum of a geometric series whose common ratio is x times e to the minus x. And one apologies for what I have said is this is not a rational function, this is just a fractional function. Rational function is the form of p of x over q of x, and both p of x and q of x both of them should be polynomial. This is a rational function. I'm sorry for that. This is not a rational function. This is just a fractional function. Okay. So I can compute the summation part, which is 1 minus its common ratio x times e to the minus x, and its first term which is 1 times 1 minus the number of term is n here from 0 to n minus 1, so it's a common ratio to the nth power here. Okay, and then we have the rest part, 1 minus e to the minus x factor, and we have fractional function x over 1 plus e to the nx power here. To figure out each target function, I'm going to separate two cases here. So when x is strictly positive, let me take a limit n goes to infinity, and then this and then e to the nx power goes to infinity. Okay, so this whole first term will goes to 0 here, and then what's left is this part. When n goes to infinity, x times e to the minus x here. So let's take a look at the function x times e to the minus x here. As you can see, the this is between 0 and 1 because the graph of exponential function y equals e to the x goes like this. Y-intercept is 1, okay, and the graph of y equals x is diagonal line here. So always e to the x is bigger than x when x is strictly positive here. So when n goes to infinity, this whole term goes to 0. So what's left is 1 minus e to the minus x power times 1 over 1 minus x times e to the minus x. Okay, so this will be our target function when x is strictly positive. So let me arrange this term. So our target function for the strict positive region of x, 1 minus x to the e to the x power minus e to the x power over 1 minus x times e to the minus x power. Okay, and then when x equals to 0, and then we just plug x equals 0 into here and into here. Okay, and then the first term goes to 0, and then for the second term, this part is 1 minus e to the 0 power is 1. So 0 times something gives you always 0. So for the target function, f of 0 should be 0. And then if you just plug x equals 0 into this target function here, since we have 1 minus e to the minus x power here, so this will also goes to 0. So the conclusion is whether x is 0 or bigger than 0, the target function 1 minus x to the 1 minus e to the minus x power over 1 minus x times e to the minus x power covers each target function. Okay, so our target function for the non-negative x here, we have this target function. Okay. The second point is to control the remainder part, the norm of each remainder, say f of x minus f sum n of x and its norm. Okay, so first let's see what is f of x minus f sub n of x is. This is difference of these two functions here. Okay, so 1 minus e to the minus x power over 1 minus x times e to the minus x power, and then f sub n of x part is minus x over 1 plus e to the nx power minus 1 minus e to the minus x times 1 minus x times e to the minus x and its quantity and the power over 1 minus x times e to the minus x. Okay, and as you can see here, this term and this term is cancelled out. Okay, so what's left is, so this term and this term are cancelled out. Okay, so what's left is minus x over 1 plus e to the nx power. 2 minus gives us a plus 1 minus e to the minus x times let me write this one as x to the nth power times e to the minus nx power over 1 minus x times e to the minus x power and its norm here. So the question is, how do I control this norm with respect to indices, subindice n here, if uniform convergence is correct? First, I have to deal with this norm by triangular inequality here. I'm going to separate each term and sum of each norm, x over 1 plus e to the nx power plus 1 minus e to the minus x times x to the n e to the minus nx over 1 minus x times e to the minus x power here. And then for the first term here, this is equal or less than e to the nx x over e to the nx power because the denominator is smaller for this case. And then if you take a look at the function, this function x over e to the nx, and if you take derivative with respect to x of this function, and you will have common factor e to the minus nx, and this derivative has a local maximum when x is 1 over n. Here its derivative function has the sign like this, okay? When x is bigger than 1 over n, the sign of its derivative becomes minus, okay? So its local maximum is obtained when x equals to 1 over n. Here we have 1 over n over e here, which is the same as 1 over n times e to the minus n power. So this value is always equal or smaller than 1 over n times e to the minus 1. Because when x is 1 over n, this is not only a local maximum, but also it's a global maximum, because for the case of x equals 0, this value is 0. 0 over e to the 0 is 0. So the boundary value is 0, which is less than this value, okay? So this is a global maximum on its domain. Okay, let's go to the second term. Since this part is between 0 and 1, okay, so this norm is less than or equal to norm of x to the n power e to the minus nx power over 1 minus x times e to the minus x power here. And for the denominator part here, this function, let me take a derivative with respect to x, 1 minus x times e to the minus x, and then I have the derivative of this constant is 0, and then minus 1 plus x times e to the minus x, and the sign of each derivative, it changes on the boundary of x equals 1. So it changes from plus to negative here, okay? So this is our local maximum here. So when x equals 1, the value for this function is 1 minus e to the minus 1 power here. For the boundary value, when x equals 0 here, we have 1 minus 0 is 1. So 1 is bigger than 1 is bigger than I'm sorry, this sign should be the opposite here. So this sign should change from negative to positive here. So this value is local minimum here, and then as you can see, this local minimum is less than its boundary value, so actually it's a global minimum here. So I can safely say that this denominator is smallest. Its smallest value is 1 minus e to minus 1 power. So what's left is only the nominator part here. So for the nominator part, I will do the same thing. Let me take x derivative with respect to this function, nominator function, x to the n power times e to the minus nx. And what I have is n times x to the n minus 1 minus n times x to the n power e to the minus nx power. And I'm gonna factor out the same vectors, which is n times x to the n minus 1 power. Okay, what's left is 1 minus x times e to the minus nx power. So the change of sign of each derivative, it changes when x equals 1 here, from positive to negative here. Okay, so when x equals 1, this is a local maximum. Okay, and its specific value is when x equals 1, we have 1 times e to the minus n power. For the boundary value, when x equals 0, its value becomes 0. So when x equals 1, this value is bigger than its boundary value. So actually this is a global maximum value. So I can say that this norm is less than e to the minus nth power over 1 minus e to the minus 1 power here. Okay, so let me arrange this normal remainder part here. So through the triangle inequality and take the derivative to figure out its local maximum or local minimum, what I have is this norm of this remainder part is equal or less than 1 over n times e to the minus 1 power plus e to the minus n power over 1 minus e to the minus 1 power here. So this part is independent of x, which means whenever n is big enough, then this can be smaller enough, say smaller than epsilon. So when n is big enough for a given positive value, this capital N only depends on epsilon here. The norm of this remainder part can be smaller as you want. So this justifies uniform convergence of f sub n of x to its target function f of x, which is 1 minus e to the minus x power over 1 minus x times e to the minus x power. For the integration part, let me give you a short comment on this integration here. Since this sequence of function is uniformly converging to its target function, okay, so the limiting value of this integration is the same as integration of its target function. It justifies because the sequence of function uniformly converges to its target function f of x, and our target function here is nothing but 1 minus e to the minus x over 1 minus x times e to the minus x dx. What's good news is it has an antiderivative. I have to do something first. Let me multiply e to the x both on the numerator and denominator, and I have integration from 0 to 1 e to the x minus 1 over e to the x minus x. It looks better. Okay, so in this case, the derivative of denominator, which is e to the x minus x, is e to the x minus 1, which is the numerator here. So its antiderivative is ln of absolute value of e to the minus x power minus x. And you can compute this value by yourself. Okay, this is all.